We collect massive amounts of data to understand society. Thousands of survey responses swirling into our servers, representing real people, real opinions, and real lives. It's easy to load that mountain of information into a statistical program and assume the computer will do all the heavy thinking for us. But statistical software like PSPP is a fast, blind calculator. It has no internal understanding of what the numbers you feed it actually represent in the real world. Take a variable like sex. If we assign the number 1 to males and 2 to females, the computer treats those as literal values. To the machine, adding 2 males mathematically produces a female. It outputs an average sex of 1.5. Technically correct, but logically absurd. The software is also blind to response bias. If a national survey receives an overwhelming response from just one state, like Utah, the program won't raise a red flag. It will simply crunch the numbers and present Utah's specific cultural outlook as an accurate reflection of the entire country. To prevent these errors, the analyst must intervene before the analysis begins. We have to act as the translator between the messy reality of people, using survey weights, and the rigid logic of math, using levels of measurement. Fixing the who is our first priority. Even gold standard studies like the General Social Survey face response rate problems because certain demographic groups are consistently harder to reach or less likely to answer a survey than others. We correct this imbalance using survey weights. This mathematical adjustment weights up the underrepresented groups and weights down the overrepresented groups, bringing the sample into alignment with the actual target population. This table shows survey responses with the weights turned off. The frequency column displays whole numbers, like 799 and 546. We keep weights off when reporting the raw sample size, or RN, to show exactly how many real-world individuals provided an answer. However, the raw sample size is rarely the main story. When we run our actual analysis and report percentages, we must turn the survey weights on to ensure those percentages represent the whole country. Look at the updated table. The frequencies now contain decimals, signaling that the software is adjusting the weight of each respondent. These weighted percentages are what we ultimately report, as they provide a better representation of how adults across the U.S. actually feel. You must distinguish these from raw weights. A raw weight multiplies your sample size until it matches the literal population of the United States. If your software thinks you have 300 million respondents, every single test you run will appear statistically significant, even if no real relationship exists. In this course, we use normalized weights. These adjust the internal proportions of the sample to reflect reality without fabricating millions of fake respondents. Once the people are accurately represented, we have to fix the math. We do this by defining the level of measurement, which tells the software the shape of the data so it can select the correct mathematical test. First is nominal data. These are simple categories with no mathematical order, such as a respondent's race, sex, or religious affiliation. Next is ordinal data. These categories can be ranked in a logical order, but the distance between the points isn't equal. A Likert scale ranging from strongly disagree to strongly agree is a classic example. Finally, we have interval ratio data. This is true numerical data, where the spacing between every point is perfectly equidistant. Age in years or years of education are both interval ratio, because the difference between 1 and 2 is exactly the same as the difference between 20 and 21. To identify these quickly, use the "does it mean well" trick. If you can calculate an average that makes logical sense, the data is numerical. An average age is a meaningful number. An average race is a statistical impossibility. This classification determines your entire analysis. If your dependent variable is interval ratio, the software should run a t-test, an ANOVA, or a linear regression. If your dependent variable is nominal or ordinal, those numerical tests are no longer valid. You must route that data through a chi-square or a logistic regression instead. If you misidentify the level of measurement, the software will still run the math, but the results will be meaningless, invalidating your entire study. This technical precision provides the essential groundwork for the most difficult task in sociology, proving causality. To show that an independent variable is actually driving a change in a dependent variable, we must first ensure our data structure is sound. A causal link is only as strong as the integrity of the data. You cannot prove why a social phenomenon happens if your sample represents the wrong people or your analysis relies on the wrong mathematical formula. Survey weights secure the validity of your population, while levels of measurement secure the validity of your math. Mastering these settings moves the analyst beyond simply operating software. It places you as the critical intelligence behind the machine, responsible for transforming raw, noisy numbers into undeniable sociological facts.